All right, so we're going to look at another lecture in Specialist Maths, lecture 29, angles, distances and intersections between planes and lines and that sort of stuff. So by this point it's getting very technical, but this in some sense is what we've been building up to because we're going to be drawing on all the information we've learnt in these other lectures to solve some problems that are a bit more practical, just in terms of finding distances and intersections and things. So introduction to vectors, resolving vectors into rectangular components, the dot product between vectors, vector equations of lines, intersections and skew lines, the cross product, as well as equations of planes will all be very useful for this stuff. And the stuff that we will look at is the distance from a point to a plane, and we'll look at the proof of that, the distance of a plane from the origin, the distance between two parallel planes, the intersection and angle between planes, the intersection of a line and a plane, and the distance between two skew lines. Okay, let's jump into it. The first thing we're going to look at is the distance from a point to a plane. And yeah, let's see if we can make some sense of it. Over here, we've obviously got this diagram going on. We'll explain what that's all about in a moment. So the distance from any point to a plane is calculated as follows. If you've got some point P and you want to get to some plane, which we use this capital pi to mean some plane in space, it's given by d, d being the distance, is equal to the magnitude of P, the dot product between PQ and the unit vector n, okay, where n is the unit vector normal to the plane and q is any point on the plane. Okay, so let's just start to wrap our head around what's going on here. So we've got our point P here. I've just put it at the origin, but just remember that it could be at any point. And then we've got some other random point on the plane Q here. This point over here is the shortest distance from the origin to the plane, which we'll talk more about in a moment. But for now, all you need to know is that this red unit vector n is the unit vector that's normal to the plane. So that's sort of the vector that's giving us the orientation of the plane. So from the situation in the diagram, we can see that the distance from P to the plane is d equals the magnitude of PQ cosine theta. Okay, and so now what we're doing is we're sort of creating triangles in our head here. And if you just think to sort of basic trigonometry, we know that the distance from P to Q must be equal to cosine of cosine theta multiplied by the magnitude of this vector PQ. And if I can get the angle right, you can see that we do in fact have a right angle triangle there. So we can sort of apply our basic trigonometry rules and say to ourselves that, okay, the distance from P to Q must be equal to the magnitude of PQ multiplied by cosine of theta, where theta is the angle between PQ and the unit vector n hat. Okay, so therefore we can see that d equals the magnitude of PQ multiplied by the magnitude of the unit vector n multiplied by cosine theta, but we know that this has a size of 1. So this is just the definition of the dot product between PQ and the unit vector that's normal to the plane. This is the definition of the dot product, if you recall from previous videos. So just the other thing to point out is the other situation is where the unit vector n hat points in the opposite direction. So it would be pointing in this direction. In this case, we will obtain that d equals negative vector PQ dotted with unit vector n. Hence, in general terms, the distance is the absolute value of the absolute value of the dot product between PQ and unit vector n. And so that's what we have here. It's the absolute value of that, because n can point in two different directions and still be the correct orientation of the plane. So that is how we find the distance from a point to a plane. Okay, so the next thing we're going to look at is the distance of a plane from the origin. So let's begin with some plane equation. So you can see in this diagram here, we've got this sort of blue plane, and that, if we were to imagine, is going to be the plane that is defined as some position vector r dotted with n, which is a vector perpendicular to the plane, and that equals k, and k is not equal to 0. Okay, what we say is that the closest point to the origin, OM, so this closest point here, the vector OM is equal to m multiplied by the unit vector that's perpendicular to the plane. And that should make sense, right? Because we know that the unit vector perpendicular to the plane, if we scale that up or down, that's going to be pointing in the same direction as the shortest distance from the origin to the plane. So you can see what I'm trying to say is that vector OM is a scaled up version, or could be scaled down version of the unit vector perpendicular to the plane. And so what we can say is then that the magnitude of m, aka how much we scale it up or down, is the distance from the origin. And so since m lies on the plane, we can say that we're essentially taking the dot product between this vector and the unit vector n, okay, where n is a vector that points perpendicular to the plane. So we end up with this situation. We know that when we multiply from previous videos a unit vector, and we take the dot product between a unit vector and a vector, we get the magnitude of that vector. And we know as well, obviously, that the dot product is associative. So we can come to this result: m multiplied by the magnitude of n equals k. Rearrange, we get that m equals k on the magnitude of n, so that is our signed distance, right? That is our signed distance to the plane. So if we wanted to take the absolute distance to the plane, we just take the magnitude of k, whatever k is. Okay, it can be quite confusing generally speaking, but in as an example, I think it'll help. So find the distance from the origin to 2x plus 3y plus 6z equals 12. Okay, just recalling, because I think it could be confusing when we're only being introduced to this. This is the dot product. So remember, this position vector r is just sort of a placeholder, right? It's saying it has coordinates x, y, and z. And then n is the vector perpendicular to the plane. So we've got 2, 3, and 6 as our coefficients, and k is obviously 12. Okay, so this here, sort of just want to drive home the point, is a representation of the dot product, because you're taking x multiplied by 2 plus 3 multiplied by y plus 6 multiplied by z, and that equals some value, in this case 12, and then that plane in blue is all the points that satisfy that equation, right? Okay, and then so we're going to use the distance formula. If we just want to know the absolute distance, we're just going to do this. We don't want the sign distance, because remember, we can end up with a sign distance which includes positives and negatives, but we don't want that. So let's work out the magnitude of n. So remember, n is this vector 2, 3, 6. And so to find the magnitude of that, you essentially apply Pythagoras in 3 dimensions. You'll get that the magnitude of n is 7. And we know that k is 12. The absolute value of 12 is just 12. So we get that m equals 12 on 7, which is approximately 1.71. And now hopefully we've fully explained this diagram here, which shows that the distance from the origin to that point m, which is the closest point on the plane, is in fact 1.71. So yeah, interesting result. All right, so the next thing we'll look at is the distance between two parallel planes. So in that situation, it's sort of what we've got going on over here. These two planes are parallel to one another. And sort of we'll look at the general theory here. So imagine you've got some plane pi1, which is r dot n equaling k1, and plane 2 is r dot n equaling k2. The normal vector n is the same for both planes. Okay, so remember, if the planes are parallel, then they're oriented in space the same way. So this vector n is going to be the same for both planes. And basically, this is the distance formula. You take the magnitude of k2 minus k1 and you divide by the magnitude of this vector n. So I think it'll make more sense with an example. So let's look again at an example here. So find the distance between 2x plus 3y plus 6z equals 10 and 2x plus 3y plus 6z equals 4. So we can see that these planes have the same orientation in space, right? 2x plus 3y plus 6z on here in plane 1, and 2x plus 3y plus 6z in plane 2, but they equal different things, so they're parallel. So we can see that k1 is 10, k2 is 4, and we know that the perpendicular vector n is, so the normal vector n, perpendicular vector, same thing, is 2, 3, 6. And so we can apply this formula. So we get that the distance formula is m, take away these from each other, and then divide by the magnitude of n. Again here, turns out that the magnitude of n is 7. So you get 4 minus 10, the absolute value of 4 minus 10, which is 6, divided by 7, which is 0.86. And sure enough, the distance between these planes here turns out to be 0.86. So interesting results. All right, let's look at the intersection between planes. So we've got that the angle between planes is given by this, and the direction vector of the intersection is given as the cross product between the two normal vectors. And the vector equation of the line of intersection is given by this business here. I just want to explain just this top part. The angle between planes. So this is just a rearrangement of the dot product. Okay. We know that when we take the dot product between two vectors, say A and B, vector A dotted with vector B is equal to the magnitude of A multiplied by the magnitude of B multiplied by cosine of the angle between them. So when we've got two normal vectors, aka our two planes in space, you can see over here we've got two planes in space, purple and blue, and they've got normal vectors that orient them in space. So we know that n1 dotted with n2 is equal to the magnitude of n1 multiplied by the magnitude of n2 multiplied by cosine of theta. So if you were to rearrange that for theta, you would get this. So that's where that comes from, as finding the angle between two planes. So just so we're clear again, whenever we have two planes, they might intersect if they're not parallel, and then we want to find sort of the angle between them, right? Okay, the direction vector of intersection, that should make sense that the direction vector of intersection is the cross product between n1 and n2. Again, you've got these two planes intersecting. We know that the direction of the vector of intersection is going to be perpendicular to both of those. So remember, our cross product is our right-hand rule. So we take our two normal vectors to the planes, to their respective planes, and we cross them with each other, and then that's going to give us the direction of the vector of intersection. And you can see here, maybe I'll just have a play around here, the direction of the vector of intersection. This is our vector of intersection in this case. You can see how it traces out the line that's on the intersection between them, right? We'll talk more about this in a moment when we look at the actual example, but you can sort of hopefully start to get the idea. Okay, just so you can understand this diagram a bit more as well. This vector here is the normal vector to the blue plane, and this vector down here is the vector to the purple plane. See, it's at right angles to the purple plane. Okay, so yeah, this is obviously this example. So plane 1 is 2x plus y minus z equals 4, and plane 2 is x minus y plus 2z equals 3. Okay, the direction vector is I minus 5j minus 3k. Why is that the case? Oh yeah, if you take the dot product, if you take the cross product between the vectors 2, 1, negative 1 and 1, negative 1, 2, you'll get 1, negative 5, negative 3. So that must be the direction vector by applying this. Okay, so what we want to do now is we want to find the vector equation of the line of intersection. So what you can do is just find a point. So let's just set z equal to 0. So what we're going to get is, if z is 0, we're going to get 2x plus y equals 4, and we'll get x minus y equals 3. Okay, remember, z is 0 is a point that's going to be on both planes. So if we just set that equal to 0, we can solve for x and y to find any point, right? So we get x equals 7/3 and y equals negative 2/3. Okay, so we know that this R0 is a point on the line of intersection between the two planes, which we can define as a vector equation, which is what we have going on here. That's why this line is, why this vector is tracing out the line that represents the intersection between the two planes. And so we get that the vector equation equals, as we said here, r naught plus t multiplied by d. And so this is our vector equation, 7/3 I minus 2/3 j from here, because that's how it tells us a position when t is 0. When t is 0, we're pointing at this point here. And then obviously as we change t, change that parameter, we move up and down that line, right? Okay, just applying the angle between planes formula here, we can see that if we take, if we apply that, we get 99.59 as the angle between the two planes. And remember, just recalling that those two vectors here, this one here is perpendicular to the blue plane and this one here is perpendicular to the purple plane. So we get 99.59 is the angle between those planes, okay? Sometimes if you take the angle between two planes, you'll get given the obtuse angle. You need to remember that you need to look for the acute angle. And now I'm just thinking to myself, that looks like it's the obtuse angle between 99. Yeah, the acute angle would be less because, let me think. Yes, so yeah, I think you would agree that that must be the obtuse angle between the planes, because the maximum angle you can have between two planes is 90 degrees when they're like this. So if we needed to find the acute angle, we need to do 180 minus 99.59. Let me know if that rings any alarm bells. I think that sounds right. Okay, so now we're going to look at the intersection of a line and a plane. So we've got some vector equation that defines a line in space, and then we've obviously got some plane as well. And if they intersect, we want to be able to find that intersection. So there's a few steps you can sort of follow. And yeah, we're going to find, in fact, I'll show you the situation we're sort of dealing with this example. If we change t, you can see that this vector equation traces out a line. And we want to know where that line crosses the plane, right? So we end up with this situation. We want to know the special point where the plane and the point intersect, right? So let's think about how we can do that. So the first thing is we've got some line equation, which again is r equals r naught plus td, where r naught is a point on the line and d is the direction vector and t is a scalar. Okay, hopefully that's looking familiar by now for a line equation in vector form. And then obviously we've got our plane equation, which is of this form, the dot product between r and n equaling k, just like we saw before. If the line and the plane intersect, then they'll be equal at that point, right? So we substitute the line equation into the plane equation. So we take this and we sub it in here for r, okay? And then rearranging that, we know that the dot product has a lot of principles as multiplication, so we can sort of rearrange things and we get this. And then, yeah, once you've found t, you sub that back in to find the intersection point. And just be careful as well, if the dot product between the direction vector of the line equation and the normal the normal to the plane is equal to 0, the lines are parallel. Yeah, because, one sec, doesn't sound right. Sorry, yeah, that's right. Because D is the direction vector of the line and N is the normal to the plane. If the dot product between them is 0, then they must be parallel. And so there'd be no intersection. In any case, let's look at this example here. So we've got a intersection of a line and a plane. So we've got this line equation, 3i minus j minus k plus t multiplied by I plus 2j minus k, which again is this purple line that's sort of been drawn out in space. And our plane for this example is the dot product between r and I plus j plus 2k equaling 2. And that's what's in blue. That's the blue plane. Okay, if we do in fact take the dot product, get a pen and paper out, work it out, but you'll get this. Something like this. And then if you solve for t, you'll get that t is 2. Okay, once we know that t is 2, we just substitute t back into the line equation, and you'll get this, where you've substituted t for 2, or 2 for t, and then you'll get 5i plus 3j minus 3k. So if we set t to be 2, that point there that it's pointing at must be the point 5, 3, negative 3. And if you want to check, the x value looks like it's 5. If you look at the red part, the y value looks like 3 if you look at the green part, and negative 3 if you look at the z part. Okay, so almost there. Hopefully that made some sense. Alright, so the last part, we'll look at the distance between two skew lines. Now, just recalling from previous videos, skew lines are when two lines are not parallel, but they don't intersect, which can only happen in 3 dimensions. And so you can see here as we move this around, we've got these two blue lines. If I get the angle just right, you can actually see that they never intersect, so they are in fact skew lines. And basically our job is to find the intersection, sorry, not the intersection, we're trying to find the distance between the two skew lines. Okay, the minimum distance, obviously. So that's going to be this distance here. Yeah, and this is how we sort of do it generally. We've got two lines, R1 and R2, or line 1 and line 2, defined by these vector equations, R1 and R2. Okay, the unit vector perpendicular to both lines is given by this, the cross product between the two direction vectors divided by the magnitude of the cross product between those two direction vectors. And then the distance between the skew lines is given by this, the position vector of R2 minus position vector of R1 dotted with the unit vector n. Okay, I realize I'm not giving a very in-depth explanation of why that's the case. I can put a link below to explain in more detail why that's true. But let's look at an example of the application of that. Yeah, so if you've got two vectors here, these vectors, if we wanted to know the distance between the two skew lines, we need to find the cross product of the two direction vectors. It will give you I minus j plus k. Step 2 is that the unit vector is perpendicular to both lines, so we need to find the unit vector n. So it's just going to be, so maybe I can explain it in a bit more detail. I've got two lines, right? And then if we want to find the cross product between them, we need to find the line that's perpendicular to both of them, because if you find the line that's perpendicular to both of them, where they intersect on that line, which in this case is here, will be the minimum distance between them. And then so what you do is you find the unit vector of that, so you divide by root 3 in this case, and then you can apply this rule, a2 minus a1, the magnitude of a2 minus a1 dotted with the unit vector n. Yeah, and then you get this, and you crunch the numbers, and you'll get approximately 0.577 in this case, which is what we have here. Okay, so we have this distance being approximately 0.58 between those two skew lines. Yeah. Yeah, so this is the reason. I should have explained it better, but the magnitude of the projection from point P to A2 onto the unit vector n will give the distance, which is the dot product between PA2 dotted with n, and yeah, and we know that that is equal to this, and then yeah, it's hard to explain. Yep, but that's the reason. Grab it, it's in the Specialist 3 and 4 textbook if you want to see a picture of it, which will help you understand why the distance between two skew lines is given by this formula. All right, good luck. If you found this at all helpful, give us a thumbs up, and good luck with everything you're doing. I'll talk to you soon.